All right, thanks everybody for organizing this. It's a pleasure. It's the first time I do this. So I'm sharing my iPad. If there is any connection problem, let me know. I changed the title with respect to the one I proposed a couple of weeks ago. I tried to make a kind of a broad overview of work that has been going on in the last few years with a number of collaborators. Daniele, Raffaello, Luigi, Giacomo from my group in Genova, especially Alessandro Rudi from Paris and others, Barath, Nick, Alessandro, and Mikkel. So the overall theme is this idea that one of the great challenge in current machine learning, it works really well, but it's very demanding from a computational point of view. So we always have to struggle finding computational resources. And the idea of trying to find ways to keep the good performances while provably reducing the computational cost is largely a challenge. And is perhaps not the top priority of industries that have large computational facilities. So the attempt here is to somewhat investigate ideas in the direction of keeping good performances while reducing computational costs. So as I said, I kind of give a long overview, and I'm going to be switching among different topics, and depending on time, I might skip some of this. So the first thing is to introduce the main idea. It is what I call the Nyström random projection. So it's a form of random projection which is data-driven. And here what I'm going to do first is going to introduce them and then provide different views. On the one hand, this might confuse some. Hopefully this will also be a way to, for each one of you, depending on the different background, to somewhat find your favorite way to look at the problem. So the basic idea is that we start from the basic observation that we call X hat the sorry, I see stuff happening now. Okay, so we call X hat the data matrix, and we think of a data matrix where n is the number of data points and d is the dimension of the data, so they come in a natural vectorial form, and we think of both n and d be extremely large. Okay, and the big observation is that oftentimes dealing with such big matrices, it's extremely cumbersome, especially for memory constraint, because in some sense handling this matrix, storing this matrix becomes a problem. So a very simple idea, the idea I start from, is the idea of reduced dimensionality. So the idea is that you're going to hit your matrix at the right with the matrix that I call here S. This matrix has the same dimension of the dimension of the data points, but is much smaller on the other side. So you should think capital M to be small and potentially much smaller than N and D. And of course, what you get is the matrix that I call X hat M, where M is there to remind you that this is the data matrix, but now the dimensionality is reduced from D to M. Okay, so that's the basic idea. Examples, of course, exist of such kind of matrices. Perhaps the simplest and most standard one is PCA. So you take the input data matrix X hat, the original one, you would have to perform a singular value decomposition, and then you could use the first M components, first M right singular vectors as a projection matrix. Of course, this is standard, there's a lot of nice properties, but computing PCA is itself costly, okay? So one idea is to somewhat try to get faster projection and faster dimensionality reduction by introducing random stochasticity, okay? And one simple idea is to assume the matrix S to be a random matrix. A simple example is a matrix is D by M, and where each entry is a standard Gaussian. Okay, so it's a Gaussian with the zero mean and variance 1. This is, if you wish, is the idea related to celebrated Johnson-Lindenström's lemma, and it's somewhat connected to the idea of what is called sketching. The kind of projection I'm going to discuss today are a little bit different, and so here I'll try to explain the notation. The idea is that we choose as the matrix S not something random, but something random obtained from the data themselves. So we're going to select a subset x1 bar, xm bar of the data points, we're going to stack these into a matrix, and then we're going to use this matrix as our sketching matrix, as our projection matrix. So X hat is the data matrix, the original one. X bar M is a matrix which is n by m. I pick among n points, m of them. Sorry, it's the matrix X bar is m by d. So I pick m among n points, each one of dimension d. If now I use X bar M transpose as my sketching matrix, I obtain a new matrix. I call it again X hat M. And if you wish, this is the matrix where each data point is now represented with the similarity between the point itself and one of these M centers, X1 bar, XM bar, okay? So a couple of observations. Clearly computing this is very efficient. You just have to subsample a bunch of points. Notice that we are not throwing away data, so we're not subsampling the data set. We are only using a subsample of the data to summarize the information on the full data set. So this matrix X hat M is still, maybe I can do this. So this matrix is still n by m. So I still make use of all the data points, okay? Now, an account where this idea comes from would require a very long story. Here I just put a set of people that have been looking at this kind of ideas. It has been proposed in the context of Bayesian statistics, in the context of kernel methods, in the context of theoretical computer science, where people look at sketches, in the context of numerical linear algebra in combination with stochastic methods. And here I just want to draw some conclusion in the context of machine learning. Before I do that, maybe I can tell you, we can try to illustrate this idea in a bunch of different ways. And I'll use least squares as a simple setting to illustrate how to use this kind of projection. So this is the basic least squares algorithm. So I have to solve a linear system defined by the data matrix and a set of output vectors y hat, okay? So when I consider now the projected data, what I'm doing is that I'm actually replacing the original matrix X with this reduced matrix, X hat M, and I'm now replacing the variable. They're not no longer the W that I introduced before, they're not D numbers, but actually this vector I call C, which is just M numbers, okay? Sorry, let me do this because it annoys me. Okay, so of course now I reduce the size of the problem, and so I expect to have some savings. Before doing that, we notice that we can actually rewrite the problem in the following way. Essentially, we are constraining the least square problem to now find solutions within a subspace, which is random, okay? So in this last expression here, you'd see that the problem on using the sketch data is equivalent to a problem where I use the original data, but I restrict the search for a solution on a subspace, okay? In a finite dimensional space, subspace of dimension M, which is random because it's the linear combination of the point I selected, or the points I selected. And if you're familiar with inverse problems, this idea relates to projection methods that are often used to discretize or find finite dimensional version of infinite dimensional inverse problems using quadrature methods, using projection methods, using things like Galerkin methods, and so on and so forth. So this is one first connection. We can view this kind of data-dependent adaptive sketching as a form of least squares on combining least squares and projection on subspaces which are random. Another observation is that we can draw conclusion from a computational point of view. We can, of course, solve the original least squares problem. We'll have to deal where I'm thinking of a situation for the case of utility where D and N are both large, but D is larger than N. So this is the case where the W admits this solution. So they are a linear combination of the input data, and the coefficients are given by the inversion of this matrix here. I'm just rewriting the form of the pseudo inverse in the case where n is large but smaller than d. And if now I write the same kind of equations for my reduced linear system, the one where I use the projected data, then I obtain the expression of C is now given by this expression here. It takes like one line of computation to recover this expression, so there's nothing interesting going here. But the point is that the matrix I have to invert is now m by m, where m is the projection size. So this is much smaller, and indeed you can do a quick check that you can essentially break the complexity, which is usually at least quadratic or cubic in the number of points, and now becomes at most quadratic or, or even less. Okay, so this is the one basic idea. This is the reason why this is useful. So another line of thinking about this is clear if we now consider a slightly broader setting, rather than just restricting ourselves to linear least squares, we can consider now kernel methods, okay? And I'm gonna give a very simple introduction to this idea. So the basic dictionary is that what the basic idea is that we want to do a bit of correspondence, and every equation I wrote before, I want to now rewrite with the following, what is sometimes called the kernel trick. So every time you see an inner product, you have to replace it with a kernel. The kernel is a function of two variables. It's symmetric and positive definite. And if you want to keep an example in mind, just think of a Gaussian kernel. So if we now play this game, a second ago, we gave this expression on the left. We said that W is X transpose C, which means that when you compute X transpose W, meaning the f of X, you get this expression on the left. If now I replace kernels, if I replace inner products with kernels, I obtain that functions can now be written as a linear combination of kernels at the training set points. So the obtained solution is not only a linear combination of the input points, but its values are actually a linear combination of inner products with respect to the input points, and we can replace these inner products with kernels. If we now write explicitly the expression of these coefficients in the linear combination, we have to introduce a linear system defined by the Gram matrix of the data as before. And the Gram matrix, if we replace inner product with kernels, becomes the kernel matrix, okay? So if you look at the expression of f of X and the linear system that gives the coefficient C, defined by the kernel matrix, you see that all you need is to be able to evaluate the kernel matrix at every pair of points. And so given this prerequisite, then you can somewhat transform the linear least squares discussion I did before into a discussion for kernel methods and nonlinear extension of least squares. And so what you gain is that rather than be forced to discuss about the linear functions, you can now fit your data to nonlinear functions, simply choosing your kernels and then deriving the set of points, the set of coefficients C. Notice that there are gazillion ways to introduce reproducing kernel space. Certainly this does not make any right to the beautiful math behind them, but this is presumably the simplest and more basic introduction. And it's literally only based on noticing that the expression we wrote for linear least squares depends on inner product that can be replaced with kernels. We can now look at in this context at the effect of this kind of data-driven projection that I call Nyström projections. So this is the summary from a computational point of view of what I just described. The first line is what you have when you have the Nyström projection. Oh, sorry, when you have just basic least squares, okay? Linear least squares. And then from the arrow down, this is the equivalent situation when you have kernels. So in the drawing, you see that what you have to deal with is a big linear system where the matrix is the size of the data set, of the cardinality of the input data. So if you have n points, then this matrix is going to be n by n. And the clear, aside from being able to solve the problem, you have to be able to somewhat store the problem efficiently. And this is the main bottleneck here. When the matrix start to be order of, say, 50,000 to 50,000, then it doesn't fit most memory, okay? And when you go to 1,000,000 points or 100,000, even 100,000 points, you cannot literally run this stuff anymore unless you swap and recompute this on the fly all the time. And recomputing the whole matrix is too much. So if now you just, again, do the dictionary and translate the Nyström projection setting into this setting, what you have is that the first line is, again, what I described at the beginning. Remember that x hat m is the data matrix now projected on m points, okay, of the training set. So is this data matrix projected on a set of random points. And what you have is that now the solution is no longer a linear combination of kernels at all the input points, but simply on a subset of them. So this is the way you can now interpret the projection methods based on subsampling the data in the context of kernels. We somewhat restrict the search for solutions to a subspace spanned by the kernels at the subset of points we sampled. And the linear system is given by this matrix K hat M. Remember, I introduced it before. This was simply the matrix, okay, given by the data matrix hit on the right with this sample matrix. So this is just a sketch matrix. Of course, this can be expressed in terms of kernels if I use kernels. And so what you see is that at this point you have to, in this kernel context, you can see that you reduce a smaller system, okay? Rather than having to solve the system where you have the n by n matrix, effectively you replace the big matrix k hat with a smaller matrix k hat nm, okay? Which you can think of a matrix that you obtain by randomly subsampling columns of the original kernel matrix. Clearly, so a few observations are useful. Clearly, you don't have to compute the whole kernel matrix and subsample it, but you can just directly compute the kernel, a subset of columns. So, of course, this is very efficient. Second, my drawing sucks just because I'm not good at animations, but you don't have to pick the first m columns. You can pick them at random, okay? Or you can pick in any order you want. And so typically we're gonna look at a situation where you pick them uniformly at random. And here I just highlight the first leftmost part for the sake of simplicity in my drawing. Third, the idea of doing column subsampling is again a standard idea in randomized numerical linear algebra. And this is one potential way to see it. It's a standard trick in machine learning where it typically goes under the name of the Nyström method or the greedy selection methods. As it is clear from this picture, the moment you replace a huge linear system defined by k hat by the much smaller one defined by k at n, nm, and m here are the size of the matrix, you get a huge computational saving. All right, so I gave you the linear least, I introduced these data-dependent matrices. I look at the linear least squares perspective, and then we did this translation from linear least squares to non-linear least squares using kernels. Before asking about the properties of these methods, we're gonna ask the question of why the hell are they called the Nyström method, okay? Rather than data-based sketching or something. So this is just a side remark. So Nyström approximation is a typical, introduced as a way to go from an integral equation to a linear system. And so here you see on the left, I define an integral equation defined by kernel. And the idea is that now there are more sophisticated way of doing it, but the basic idea is that you can discretize this expression by taking a set of quadrature points, okay? And replacing the integral with a sum. And this is a basic version of the Nyström approximation. Now, if you can, of course, replace this idea if rather than an integral, you have a huge sum, okay? And now you want to replace the huge sum by a smaller sum. So if you look when I say going from operators to matrices, I don't have an integral anymore, but I have a huge sum, okay, of n points. And effectively, what I can do now is that I can replace the set of centers of this equation with a subset of centers. So I still have to evaluate this linear equation on a lot of points, but now I select a subset of points. So instead of going from an integral to a sum, I want to go from a very large sum to a smaller sum. If you rewrite this last expression in matrix notation, you obtain simply these two systems I showed you before. A big linear system, where in some sense I do a first set of quadrature, and then a second linear system, which is the smallest version of this. So in some sense, this is applying the idea of the Nyström approximation of integral equations to large matrices. Okay, and this somewhat justifies the name. All right, so this concludes somewhat the first part of the talk, where the idea was that we were going to introduce these projections and provide several perspectives of them. So at this point, hopefully what you have in mind is that this is a way to perform PCA or something like PCA without having to perform the heavy computation of PCA. You can view this from a sketching perspective, from projection perspective, from color subsampling, from the discretization of integral equation perspective. No matter which point of view you like, it's clear that you can reduce dimensionality and savings and have computational savings. And the question now becomes if and how much you will lose from an accuracy perspective. So from a learning accuracy perspective, okay? And so this is what I want to do next. This will be the time where I ask if there are any questions, but it's hard in this modality, so I just will drink instead. And breathe. All right, so the first context where I want to ask the question of what is the price I pay by doing this kind of projection is that of supervised statistical learning. Here, we assume to have input and output data, and the data to be sampled according to some probability distribution. We call it learning because we would like to minimize the error with respect to this distribution, in this case, the least square error. But the problem is that I do not have access to the distribution, but only to a subset of points that are sample IID, identically independently with respect to this distribution. So the learning problem comes from the fact that we only have finite data, but we ideally would like to minimize this expectation. And the interpretation is that this expectation can be thought of as a future error the error on future data, or a test error. All right, so the basic idea is to consider exactly what we consider. We don't assume in general to have invertible matrices, so we're going to look at instead of the case where we have to regularize the matrix by adding a diagonal element to the matrix inversion. Now, this is what you might call Takehome regularization or ridge regression, regularize these squares, Gaussian process regression. From our perspective, it's just that it's the exact same algorithm I showed you before. It's based on kernels, and rather than just inverting the kernel matrix, it actually utilizes a parameter lambda to make the matrix invertible or well-conditioned, even if it's not so. So I denote by f hat lambda this empirical solution based on inverting a regularized version of the matrix. The properties of these methods are standard, okay? They're well known. And what we know is that if we now use this to solve the original problem, so we ask, how much is the expected error of this solution? Then we have to specify a choice of the parameter. And in the basic form, if we choose the parameter of the order of 1 over square root of n, then we get the bound of 1 over square root of n. This is a very basic result. The interesting part of this is that under this assumption, this result is optimal. It cannot be improved. It can be improved and refined in a bunch of different ways if we add further assumption. But in some sense, we want to keep the presentation simple. And so this is our gold standard. We know that if we are willing to solve the full linear system, then we can get these statistical bounds. The question we want to ask is what will be the bounds we obtain if we replace the full kernel matrix by the one obtained by doing these Nyström projections. So in this setting, the Nyström projection, again, have this extra regularization term. We have to replace the identity with this k hat mm, which is the square matrix obtained comparing the center with themselves through the kernels. The details are not so important. What is important is this result that says that with the exact same choice of the regularization parameter, so the algorithm is simply the Nyström projection I showed you before, just in this regularized setting. And the basic result shows that with the exact same choice of the regularization parameter, if I pick the projection size, order square root of n, and here the points are chosen uniformly at random, then I'm gonna get exactly the same learning bounds I obtain if I solve the exact kernel ridge regression, Gaussian process, or whatever you want to call it. So there is a whole regime where I do not pay any accuracy cost while I can reduce the dimensionality substantially and hence the corresponding computations. Notice that this is in contrast with the typical study when you only study the approximation property of kernel matrix, where if you don't keep into account the fact that you have to solve a downstream task, in this case a supervised learning task, then by replacing the original system with the smaller system, you will lose. But the key point here is that your goal is not to solve this large linear system. What you want, this large linear system is noisy, both in the matrix and in the data. What you really care about is future error. So in some sense, you don't need to solve it exactly, but you only need to solve it at the precision that is allowed by the data. And this is the main intuition behind this blessing of being able to save computation without incurring a computational cost. Now we can improve these results because of course why not want to solve this linear system in a direct way? We might want to use an iterative solver or a precondition, possibly with the preconditioning. Preconditioning this full matrix, this rectangular matrix will be extremely costly because the basic preconditioning would correspond to actually invert this matrix. And so one possibility is to rather than do the preconditioning exact by creating the inverse of this rectangular matrix, we can only we can stall the linear system for the rectangular matrix, but only take a small square part to compute an approximate precondition. So this is the best solution we have so far. We solve conjugate gradient with 2 rounds of projection. The first is to go from the big linear system to a smaller one. The second is to go from this smaller linear system to even smaller matrix that we only use for the precondition. With this choice, what we have is that not only we can give a guarantee in terms of the memory needed, but we can also tell exactly how many iterations we need to achieve optimal statistical accuracy. So these results mixes up optimization in statistics. I don't ask what is the rate to go to convergence. I ask what is the rate to get the optimal statistical bound. This is what we call Falcon, and it provides one of the fastest large-scale, or perhaps the fastest large-scale solver for kernel methods and Gaussian processes. So this is the basic result. And if you look at the last line, what it shows that if you can now compare the full kernel ridge regression, basically you have that from a statistical point of view, if you replace it with this algorithm that we call Falcon, you pay no statistical cost, but you go from a quadratic memory cost to a linear quadratic cost, and you go from a cubic cost to something which basically is n square root of n, okay? Which presumably is close to the optimal complexity. Just to conclude, you can implement this stuff and you obtain solver for kernel method that scale to millions of points, okay? They run on a single GPU machine and they can run in seconds, okay? Just by essentially projecting. And essentially in this table that I'm gonna share with you, essentially we compared with all the algorithms that we found that were tried on this data set, there are 1 million or more points, okay? So classical algorithm setting where typically you don't run an SVM-like algorithm for lack of scalable solver. And here what you see is that our algorithm work always as best, has the same accuracy, but often only a fraction of time. And you can further go to datasets that are the biggest datasets around that are one in high energy physics, in which case we can actually run the algorithm up to 11 million points, which is the largest we have. Right, so this somewhat concludes the second part of what I wanted to tell you about, okay? The take-home message here is essentially, these Nyström projections provide a way to
approximate a problem, okay? But the problem itself is actually only a reflection of an ideal problem where we have infinite data and we want to do prediction. So we don't need to project with an accuracy which is bigger than the one that is allowed by the sampling noisy data, okay? And once you figure out how much is this projection that allows to keep the exact useful information in the data, you discover that you can actually have good statistical accuracy with only a fraction of the computational cost that we incurred before. So the natural question is to which extent these results are specific for this setting I consider. And now I want to introduce a different setting, very different, but where you'll see we use similar techniques, where you'll see somewhat a similar effect. This is the setting of bandit optimization. The setting of bandit optimization is really a completely different setting. So we switch completely, is roughly speaking a setting where we want to compute a maximum of a function defined on a finite set. So the function is unknown and all we have are noisy samples, okay? So this is the basic, one basic intuition. So we have a domain that I call calligraphic A. This is a domain that you can think of as what is sometimes called the set of arms. There is a function f, which is unknown, and then there is a set of random variables eta t. I call x star the maximum of, or the maximum point, the points where the maximum is achieved of this function. And the goal is the following, is a sequential way to try to find estimate of this maximum with a very special way to measure the performance. So the idea is that we begin by making an estimate of the true function, okay? I call it u eta t, and this is the first step. At this point, we pick an arm, we pick a point in the domain, a candidate minimizer, and then we are revealed not the value of the function, which remember is unknown, but only a noisy value of the function. Based on this, we go back and estimate again, update our estimate u hat, and keep on going. Ideally, what we would like is the error to be small. And here what we do is not only that we measure the error of the last step with the minimum, but what we do is that we want to somewhat sum the errors that we have at every step, what is called the cumulative regret. So if you see, this is the sum of the error at every step with respect to the best one, summed up over the number of steps, okay? So this is the classical setting of bandit optimization. Is a similar flavor to zero order optimization. So situation where we want to study the extreme of a function without knowledge of gradients. But here there is somewhat a couple of different aspects. One is the fact that we only have access to noisy function evaluation. Two, that we're really looking into this kind of sequential paradigm. And three, we measure error with respect to this cumulative regret. In this setting, one way to do things is again based on what I call kernel ridge regression. Is sometimes here we like to think of the Gaussian processes. What is written here is essentially exactly what I showed you before, is the full kernel ridge regression estimator. The difference is that using the theory of Gaussian process, we not only look at the pointwise estimate, f at t. This is what I call f at lambda a second ago. I dropped the dependence from lambda. And besides looking at this pointwise estimate, I look at the variance estimate at each point, okay? So in the drawing, what you see is that if I have a true function in red, that of course I don't know, then I have my estimate in blue. And what you see is that where you have a lot of points, you have the blue estimates, and then you have the gray area. This is the confidence band, is plus and minus the variance, I guess the standard deviation. And what you see is that you can get somewhat the confidence bands around it, which becomes more precise when you have more data, and of course it becomes less precise when you have less data. So you have more uncertainty on the value of your function, and that's why the gray region becomes very large where we don't have a lot of points. So next I'm going to explain you how you can use this to solve the previous problem. So this is a basic Gaussian process. We have for each value, we not only have the function estimation, but also the standard deviation. We want to know now how to use this idea to solve the bandit optimization problem. So let's go back to that setting. There is a fixed function that you don't know and is here in red. In principle, you might have access to the value of this function in the arms value. So you somewhat have access to this discretized version. Remember that we will not know this, but only get some noisy version of this. So what we could do, we could collect a set of points. And here, for the sake of simplicity, I assume that I collected the first t points, okay? I'm missing the second half. Then what could we do? This algorithm called Gaussian process upper confidence bound recommend to first estimate the value of a function based on the half of the points on the arms. Then we estimate the variance. And what we have is that, again, we have the upper confidence bound and the lower confidence bounds. The idea is that we now want to consider the upper confidence bound, which is now denoted in green. And then we want to take the maximum of this, okay? We're gonna take the point, okay? We only consider this and consider the point where this upper confidence bound achieves its maximum. This is our candidate minimizer. Provided with this new point, we now get a new sample and then we repeat the technique. We update our estimate, we find again the upper confidence bounds, we update our guess for the maximum, we receive the new noisy function value, and we keep on going, okay? So this is the basic idea. The algorithm is relatively simple but clever. And essentially, it costs cubic in the number of steps and linear in the number of arms because of the fact that we have to compute the variance as we proceed. The good news is that, well, I didn't point out that, this upper confidence bound has a weight, beta t, that somewhat tells you how much you want to believe your uncertainty and how much you want to believe your estimate. And it turns out that there is an expression, not necessarily easy to compute for this beta t, for which you can characterize the regret of these techniques, which is basically square root of t. Now, the idea is that, and this becomes the same of the kernel ridge regression I showed you before. This becomes the gold standard we would like to match, okay? We have an algorithm which gives good results with high computational cost. We would like to improve on this. What do we do? Here, the first idea will be to use just the Nyström approximation. And so here, again, aside from details, this is the exact same thing I did before in general and then for least squares. The only thing I do is that I also add the variance formulation. And I use a slightly different formulation, which is equivalent to the one I used before. So I skip these details. But the problem is that in general, you can save computational cost, but it's hard to prove regret bounds for this kind of algorithm. And the intuition is that in some sense, you have to specify the set of centers, and how to do it is not clear. The data changes over time, and I need someone to adapt my centers to the changing data. So we propose the variation of this basic idea based on Nyström that utilizes, is based on basically two intuitions. The first is that we want to update the set of centers that we use to compute the Nyström. And two, that we can somewhat use the variance to decide which points we should pick. Okay, so as soon as we have the variance of all the points, we can, or an estimate of the variance, we can use this to somewhat update our choice of the points. The algorithm is obtained is exactly the same as the one before. There are two differences. One, we replace the true GPUCB with the Nyström version, and two, we make a specific choice, which is of the centers, which is now denoted in red, which is probabilistic with probabilities that are proportional to the variance. Okay, so the main ingredients are used in Nyström and selecting the Nyström centers according to the variance in an adaptive and recursive way. This algorithm, then it is possible to prove that with the center size, with the number of centers, a number of projections, which is potentially much smaller than the total number of steps, we can obtain the exact same performance that you obtain on the full GPUCB. Okay. What I denote here by df is a quantity that depends on the set of arms I have, and the kernels they can be that typically can be much smaller than the number of steps. So in practice, you can indeed do some simulation and see that you can obtain the same sublinear regret in only a tiny fraction of time. And recently we have some further improvement where we show that this can further improve using some idea such as mini batching, okay, or batching. Okay, and this is some preprint going on. But the catch here is that, again, in a completely different setting, we were able to somewhat play the same game. Replace a large problem with a smaller one and show that you can actually achieve the same kind of accuracy of the original problem as long as you take a projection size which is much smaller than the exact formulation of the algorithm. All right, I probably don't have time to do both examples, but I wanted to mention the idea that you can actually go from supervised learning or function estimation problem to unsupervised function estimation problem. And in recent years, in the last couple of years, we have had results both for kernel K-means and kernel PCA. Kernel K-means is a little bit easier to explain. So I have both in the slides, but I will explain the only kernel K-means. And somewhat give a simplified discussion. So the basic idea is that kernel K-means, as you know, is a way to partition endpoints in K clusters, okay? And it's based on this formulation where for each point, you find a closest cluster, you check how far you are. From this, you sum all the errors, and then you find the centers of the cluster that makes this distance small, okay? So this is one possible way to formulate K-means. Of course, K-means by nature only find Voronoi partitions, so clusters that somewhat have linear separation. So if you have two clusters, in the case of these two concentric circles, that are not well described by linear separation, then K-means won't work. So the idea of kernel K-means is to somewhat cure K-means by observing that K-means is based only on square distances. So square distances can be written in terms of inner products, and so you can replace the inner products with kernels. And so I won't give more details than this, but the basic idea is that, again, you can do a kernel formulation of K-means, replacing inner product with kernels, and what you obtain in this case, as you see, is that in the original data space, you don't have linear separation anymore. You have the usual perspective with kernel and feature maps, if you wish, where you map the data in a higher dimensional space, you perform K-means in the higher dimensional space, and then when you project back to the original space, the separating regions between the classes are non-linear, okay? So the exact formulation takes a bit more time than one I have here. I just want to give you this bit that if I have inner product, then I can replace it with kernels, and they will correspond to non-linear clusters. Of course, you will incur the same problem you had before, meaning that you have to deal with this huge matrix. Of course, you can again play the same game you did before, which is to replace this full matrix with only a chunk of it, okay? And again, I gloss over the details of how you do it, but the idea are very similar to the one I showed before. Again, you can immediately show that rather than dealing with a huge matrix, you only have to deal with the chunk. And then you can ask to which extent you can obtain good performances, okay? And again, you can take a statistical learning point of view. So you can assume the data to be randomly sampled, and you can measure the quality of the solution obtained by K-means by means of, if you want, the expected distortion or expected reconstruction error. So what you do is that you measure the error of the center of K-means, but not only on the training data, but on all the data coming from the distribution. So you take an expectation or X and measure the distance of all the points with the closest centers. In this case, what we have is that we can decompose the error of this Nyström kernel K-means in two parts. The first one, as you see, goes as K over square root of N and is a statistical part. The second part goes as K over M. It depends on the number of centers. This is the computational cost of doing the projection. And it's clear from this expression that you, again, if you choose M order square root of N, then you can go back and obtain the bound, which is K over square root of N. The interesting insight, and this is exactly the cost of K-means if you don't project. It's the cost of kernel K-means if you don't project. So the K square root of N is at the same time the rates of the exact kernel K-means and the one of kernel K-means with this Nyström projection if you choose M equals square root of N. In practice, you see this effect. Here, we just show a plot where the red curve is the theoretical prediction and the blue curve is what we find in practice, running experiment on MNIST datasets. And so you see that roughly when you reach square root of n as the number of centers on the x-axis, you have the number of centers, you don't improve your quantization, expected quantization error anymore. All right, so I think I'm about done. So I'm gonna skip the PCA, which has a similar flavor, and I'll leave it in the slide that I'll post somewhere. And maybe I'll just wrap up here. So again, the basic idea is that you can show that there are many situations, supervised statistical learning, bandits, clustering, PCA, where you can perform this form of data adaptive projections, reduce dimensionality, and do not incur in any statistical accuracy. Of course, you can push it more, and then you will have a trade-off between computation and statistics, but somewhat a novel fact here is that you can actually go be in a regime where you don't pay at all. There are a few results that I didn't talk about. You can discuss, okay, you always sample point uniformly at random. Can you do better than that? Yes, we can. We studied this, and in particular, Daniele Calandriello studied this. You can do what is called leverage score sampling. You can do DPP, determinantal point process sampling, and I think this is the topic of the next talk. And then you can also compare this with a more data-independent selection criterion based on more related idea to sketching, what you call random features. What can we do? Just to mention a few things real quick. You can keep on doing this game where you take your kernel methods, your favorite kernel method, and you try to do the Nyström version. At this point, we know that there are several examples where you can do this, and then immediately you should have provably guaranteed a more efficient version of the kernel methods. It'd be interesting to look at regime where you have very few points with the number of dimension. This is somewhat the interpolation regime that has been discussed and somewhat is glossed over in the analysis we have so far. And then I think it would be very interesting to take more this projection point of view and look at multi-scale projection and try to somewhat mix up random projection and multi-scale projection. And there are results in the last few years by I.M. Avron, Ricard Sindawani and colleague that goes in the direction. Just a couple of plugs. One is that there are several positions in Genova, so come work with us if you like this stuff. And I conclude here with a few relevant references of both papers and codes that implement. Okay. I think I'm done.